Hello. Today I'm going to talk about factoring trinomials of the form x squared plus bx plus c, where b and c are both integers. This process is very, very, very different than the process that Candace just showed you. If I was teaching this in a class, or Candace or Ann for that matter, we would be breaking our students up in groups and having them work some practice problems of the types that Candace showed before we'd launch into this new type of factoring process. So if you are watching this on videotape, I strongly recommend that you pause the tape right now, get out your textbook, find the problem set that talks about factoring out the greatest common factor, and work some practice problems before you watch me work this part of the lesson. Now, I'm going to begin by looking at some foiling processes and trying to identify some patterns from FOIL. And then I'm going to talk about how we can use a guess and check process to figure out how these trinomials factor. And then I'm going to talk a little bit about factoring binomials. We're going to talk more about factoring binomials next week, so that's when part 2 will come up. So let's talk about recognizing patterns that emerge from FOIL. And I think a good starting point for recognizing these patterns is to do some foiling. So let's FOIL out x minus 7 times x plus 4. There's my first product. There's my product of the outside terms. There's my product of the inside terms. And there's my product of the last terms. And when I simplify, I get x squared minus 3x minus 28. Let's think about where these coefficients on x and the constant come from. Negative 3. Where did that number come from? Well, look at the two binomials that we FOILed. The constant terms are negative 7 and plus 4. And guess what? Negative 7 plus 4 is negative 3. Why did those two numbers add to the coefficient on x? Because when I found my outer and inner products, the coefficients on the outer product and inner product were precisely the constant terms in the two binomials. How about the constant in my trinomial? Where did that come from? That came from multiplying together the constant terms from the binomial. Negative 7 times 4, the products of the last. Let's see that again. Let's make it x minus 7 times x minus 4. F-O-I-L. There's my simplification. Where did the coefficient on x come from? It came from the sum of the two constant terms in the binomial factors. Again, the two constant terms in the binomial factor ended up being the coefficients on x from my outer product and my inner product. Where did the constant 28 come from in the trinomial? It came from multiplying together the two constant terms in the binomials. Negative 7 times negative 4. I think I see a pattern. And the pattern is that the coefficient on x ends up being the sum of the two constant terms in the binomials, and the constant term in the trinomial ends up being the product of the two constant terms in the binomials. Let's see that in a more general sense. Suppose that we were multiplying x plus m times x plus n. The first would multiply to x squared. The outers would be the number n multiplied by x. The inner product would be the number m multiplied by x, and the product of the last terms would be m times n. Now, I'm not doing factoring per se in the next step. What I'm going to do in the next step is I'm going to factor x from the middle two terms just so that we can see that indeed, after we employed the commutative property of addition, the coefficient on x is indeed the sum of the numbers m and n. And the constant term in the product is indeed the product of the constant terms m and n. So we have a pattern. If b and c are integers, then the trinomial x squared plus bx plus c factors over the integers if and only if there are two integers, m and n, with the properties that m plus n equals b and m times n equals c. Now let's take a breath and look at this in a little more detail. When we are factoring x squared plus a number times x plus another number, what we need to identify is a pair of numbers m and n with the property that m plus n adds up to the linear coefficient b, and m times n multiplies to the constant term. If the trinomial factors, then x squared plus bx plus c equals x plus m times x plus n. If the trinomial does not factor over the integers, the trinomial is called prime. Now I know this is all a lot to take in, so I am going to work several examples for you. Let's factor, if possible, x squared plus 4x plus 3. Well, the first thing we need to do is we need to ask ourselves, are there two integers that multiply to 3 and add to 4? I want the integers to multiply to 3 because that's the constant term, and I want the integers to add to 4 because that is the linear coefficient. Well, let's narrow our choice down a little bit. Since we want the two integers to multiply to a positive number, the two integers in the product must have the same sign. If you multiply two positives, you get a positive, and if you multiply two negatives, you get a positive. Furthermore, since the two numbers we're looking for need to add up to positive 4, the two numbers cannot possibly both be negative. It must be the case that they're both positive. So we're looking for two positive integers that multiply to 3 and add to 4. Well, this one's pretty easy because there's only one pair of positive integers that multiplies to 3, and that's 1 and 3. And lucky for us, 1 and 3 just happen to also add to 4. So the two numbers we're looking for here are the numbers 1 and 3. So using our pattern, it must be the case that x squared plus 4x plus 3 equals x plus one of the numbers, which was 1, times x plus the other number, which was 3. I could have also written this as x plus 3 times x plus 1. As Candace mentioned repeatedly in her part of the lesson, one of the swell things about factoring is that you can always check your answer if you go ahead and multiply together your proposed factorization. I'm going to do that inside a little bit of a thought bubble here, because after you've done a lot of practice with factoring, you generally can check it in your head. So I'm going to put that idea in your head by writing my check down in a thought bubble. You do definitely, at first, want to explicitly write out all of your checks because it helps you understand the process if you write out all of your checks. So what I'm going to do is I'm going to go ahead and FOIL my proposed factorization. X times x gives me x squared. X times 3 gives me plus 3x. 1 times x gives me plus x. And 1 times 3 gives me plus 3. And doing a little simplification, I do indeed see that this simplifies to x squared plus 4x plus 3. So I found the correct factorization. Let's do another example. X squared minus 5x plus 6. We want two integers that multiply to the constant and add to the linear coefficient. So the question is, are there two integers that multiply to 6 and add to negative 5? Well, since the product is positive, the two numbers, the two integers, must have the same sign. And since the sum is negative, both numbers must be negative, because there's no way we're going to add two positive numbers and get negative 5. Well, let's start thinking about pairs of negative integers that multiply to 6. There's only two pairs, negative 1 and negative 6, and negative 2 and negative 3. Which one of those pairs of numbers add to negative 5? It's negative 2 and negative 3. So the numbers that I'm looking for are negative 2 and negative 3. Using our pattern then, x squared minus 5x plus 6 equals x plus negative 2 times x plus negative 3. But we generally don't write addition of negative numbers. We generally write addition of negative numbers as subtraction of positive numbers. So I'm going to write my two factors as x minus 2 times x minus 3. I need to check. When you first start checking, write out your check. Eventually, you want to see if you can check in your head. X minus 2 times x minus 3. F is x squared, O is minus 3x, I is minus 2x, and L is plus 6. And if you simplify that, you do get x squared minus 5x plus 6. At least if you simplify correctly, you do. All right, let's factor x squared plus 2x minus 8. In the last two examples, the list of candidates that multiplied to the constant were pretty short. Sometimes you get a lot of pairs of numbers that multiply to the constant. In that case, sometimes you need to be a lot more deliberate in your search for the pair that adds up to the coefficient. So I'm going to work several examples where I show you a deliberate method that you can use to find your two integers. In this example, we want to find two numbers that multiply to negative 8 and add to 2. Since the product is negative, the two numbers in the product must have opposite signs. You only get a negative result from multiplication when the two numbers have opposite signs. So let's think about all the pairs of numbers with opposite signs that multiply to negative 8. The methodology that I'm going to use is I'm going to begin with 1 and figure out what I need to multiply 1 with to get negative 8. And then I'm going to go to 2, and then 3, and 4, and 5, etc., until I've exhausted all of the possibilities. Well, 1 and negative 8, they multiply to negative 8. How about 2? 2 and negative 4 multiply to negative 8. How about 3? 3 doesn't evenly divide negative 8, so I blow right past 3. How about 4? 4 and negative 2 multiply to negative 8. 5, 6, 7, none of those evenly divide into negative 8. But positive 8 does. 8 and negative 1 multiply to negative 8. Now I'm looking for a pair of these factors that add to 2. Well, let's look at their sums. I can see pretty easily that the pair that adds to 2 is 4 and negative 2. So what I want to do is I want to use those as the constants in my two binomials. It must be the case that x squared plus 2x minus 8 factors into x plus 4 times x plus negative 2, which I'm going to write as x minus 2. Let's check. FOIL is x squared minus 2x plus 4x minus 8, which does indeed simplify to x squared plus 2x minus 8. Let's factor x squared plus 5x minus 24. I want two integers that multiply to the constant, which is negative 24, and add to the linear coefficient, which is positive 5. Are there two integers that multiply to negative 24 and add to 5? Since the product is negative, the two numbers in the product must have opposite signs. But this time, I'm going to cut my list of candidates in half because since the sum is positive, the positive number in the sum must have the larger absolute value. Remember, when you add numbers with opposite signs, the sign on the sum is the same as the sign on the number that has the larger absolute value. So let's look. Let's begin with 1. What do I multiply 1 by and get 24? 1 and 24. Since I want to get negative 24, I want one of the two numbers to be negative, but since I want them to add to a positive sum, I want the positive number to have the larger absolute value. So what I'm going to consider is negative 1 and 24. That sums to 23. Got to keep looking. 2. 2 times 12 is 24. So negative 2 times 12 is negative 24, and positive 2 times negative 12 is also negative 24. Since I want a positive sum, I'm only going to consider negative 2 and 12. That adds up to 10. Keep looking. 3 times 8 is 24. So the pair that I'm interested in is negative 3 times 8. Negative 3 and 8, guess what? They add up to 5. My search is over. It must be the case that x squared plus 5x minus 24 equals x plus negative 3, which I'm going to write as x minus 3, times x plus 8, which I'm going to write as x plus 8. Let's check. FOIL. X times x is x squared. X times 8 is plus 8x. Negative 3 times x is minus 3x. And minus 3 times 8 is minus 24. And all I'm really checking here is the OI part of FOIL. Do the O and I add up to 5x? Surely they do. Let's move on. Let's factor, if possible, x squared plus 6x plus 40. As soon as this problem came up on the screen, I knew it wasn't going to factor. Now, you might think the reason I knew that is because I wrote the lesson, and I suppose there's a certain amount of truth in that. But there's actually clues in the numbers here that this polynomial doesn't factor, and you want to develop a sense about these things over practice. It's going to take a long time for you to develop this sense. I'm just going to put the seed of some ideas in your head of things that you might want to think about to develop a factor sort of sense here. So, what I'm looking for is two integers that multiply to 40 and add to 6. Can you kind of see why I know this isn't going to factor? Well, let's get down and dirty with it. Let's start thinking about pairs of integers that multiply to 40 that might add to 6. Since the product is positive, I know the two numbers need to have the same sign. And since the two numbers need to add up to positive 6, that sign must be positive. So let's go through our list of candidates. 1 goes into 40 40 times, but 1 and 40 do not add to 6. 2 goes into 40 20 times, but 2 and 20 don't add up to 6. 3 doesn't evenly divide into 40. 4 goes into 40 10 times. 4 and 10 don't add up to 6. 5 goes into 40 8 times, but 5 and 8 don't add up to 6. 6 nor 7 divide evenly into 40. 8 divides evenly into 40. But guess what? We've already considered this pair of numbers. When you encounter repeats, if you're being methodical like this, 1, 2, 3, 4, 5, 6, 7, 8, etc., when you encounter repeats, it's time to give up the search. You've found all the potential pairs. None of the pairs worked, so it must be the case that this polynomial, this trinomial, is prime. Can you see now why I knew this wasn't going to work? I could see that when I took two numbers that multiply to 40, there was just absolutely no way I was going to get the weeny little sum of 6, because if you multiply two numbers and get 40, one of the two numbers has got to be bigger than 6. Now, are there two integers that multiply to 40 and add to 6? There's another way we could explore this. And the other way we could explore this is we could begin by focusing on adding to 6 and trying to find a pair that multiplies to 40. Again, I know I need two positive integers. So what are the pairs of positive integers that add to 6? 1 and 5 do, but they multiply to 5. 2 and 4 add to 6, but they multiply to 8. 3 and 3 add to 6, but they multiply to 9. 4 and 2, well, guess what? I have a repeat. And just like if you're considering the factors of the constant, when you encounter repeats, it's time to stop. If you're considering integers that add to the linear coefficient, when you encounter repeats, it's time to stop. Now again, let's look at this table. Let's look at the kinds of products we get when we take two positive integers that add to 6. We get little itty-bitty products compared to the number 40. There just was no way we were going to find two positive integers that add to 6 and multiply to 40. Again, it will take time for you to develop this intuition. I'm just putting the seeds of an idea in your head. We do need to make sure that we remember, though, to write a conclusion. Absence of a conclusion does not imply that you know that the trinomial is primed. Absence of a conclusion implies that you have no idea how to factor the trinomial. So let's give ourselves some room to write a conclusion, and our conclusion is that the trinomial x squared plus 6x plus 40 is prime. All right. Let's factor, if possible, x squared minus 7x minus 60. Now you might be looking at this and thinking, well, just like 6 and 40 have a huge difference in magnitude, so do 7 and 60. And you're right, they do. However, there's a big difference here. And the big difference is that the 60 is being subtracted. The constant is really negative 60, which means that I'm looking for two numbers that multiply to negative 60, which means the two numbers are going to have opposite signs. And that gives me a whole lot bigger chance of coming up with a sum of negative 7. So let's work through this. Are there two integers that multiply to negative 60 and add to negative 7? Since the product is negative, the two numbers in the product must have opposite sign. But this time, since the sum is negative, it's the negative number in the sum that must have the larger absolute value. Otherwise, the sum's not going to turn out to be negative. So let's run through our list of candidates. Let's start with 1. 1 and 60 multiply to 60. I want the negative number to have the larger absolute value, so I want to consider 1 and negative 60. Nope. 2 goes into 60 30 times. I want the larger absolute valued number to be made negative. 2 and negative 30. Doesn't work. 3 and 20. I want the 20 to be the negative number. 3 plus negative 20 doesn't add to negative 7. It's got a 7 in it, but it ain't negative 7. 4 goes into 60 15 times. 4 plus negative 15 is negative 11. We're getting closer, but we're still not there. 5 goes into 60 12 times. 5 and negative 12, yippee, they add to negative 7. 5 and negative 12 are the two numbers I'm looking for, and it must be the case that x squared minus 7x minus 60 factors into x plus 5 times x minus 12. And just a little reminder, I could have also written x minus 12 times x plus 5. The order in which you write your factors isn't important. Let's make sure we check, at least in the old noggin. FOIL, x squared minus 12x plus 5x minus 60. Something that's kind of nice about writing out this check is I can see why the process works. The 5 and the negative 12 multiplied to the negative 60. The minus 12 plus the 5 ended up being my coefficient on x. By the way, I did add the minus 12x plus 5x and saw that it was minus 7x. Okie dokie, let's factor x squared minus 15x plus 44. Are there two integers that multiply to 44 and add to negative 15? Well, what kind of numbers am I looking for? Since the product's positive, the two numbers have to have the same sign. But since the two numbers add up to a negative 15, the common sign on the two numbers must be negative. Let's start at 1. 1 goes into 44 44 times. What's the sum of negative 1 and negative 44? It's negative 45. 2 goes into 44 22 times, but I need both my factors to be negative. What's the sum of negative 2 and negative 22? It ain't negative 15. 3 doesn't evenly divide into 44. 4 does, though. 4 goes into 44 11 times, but I need my two factors to be negative. What's the sum of negative 4 and negative 11? It's negative 15. We're good to go. It must be the case that x squared minus 15x plus 44 equals x minus 4 times x minus 11. Doing my mental check. My firsts multiply to x squared, my outsides multiply to minus 11x, my insides multiply to minus 4x, and my lasts multiply to plus 44. And yes, indeedy doodle, my OI terms add to minus 15x. Now I'm going to talk about the guess and check method. The guess and check method is actually the very process that I've just been going through, except that I tend to, after practice, stumble upon my pair of integers a lot quicker, and I tend to be able to figure it out in my head. So what I'm going to do with the next 4 examples is I'm just going to guess what the factorization is. And something that it would be a really good idea for you to do is to work the example before you listen to me guess what the factorization is. If you need to make lists of integers, that's fine. That's the natural starting point. Almost everybody needs to do that at first. But in time, try and see if you can guess. I'm going to zip right through these examples. One thing that will get in your way of being a successful trinomial factorer is not knowing your times table. And you really should know your times table clear through 12. Now here, I'm only showing the part of the times table that includes 7 through 12. Don't think that's the only part you need to know. You need to know 1 through 12 in both directions. If you don't know your times tables up through your 12s, it's really hard to identify your pairs of numbers that multiply to your constant. For example, if you don't know that 4 times 5 equals 20, you're never going to guess how x squared plus 9x plus 20 factors, because 4 plus 5 equals 9, and 4 times 5 equals 20, and good golly, I just gave that one away, didn't I? X squared plus 9x plus 20 factors into x plus 4 times x plus 5. And in my head, when I'm foiling this, x times x is x squared, x times 5 is 5x, 4 times x is 4x, or 5x plus 4x is 9x, 4 times 5 is 20. See if you can figure this one out. This one's a little tricky. Okay, what am I looking for? I'm looking for 2 positive integers that multiply to positive 7. I know they need to be positive because they need to add up to 12. The only pair of positive integers that multiplies to 7 is 1 and 7. And 1 plus 7 isn't 12. So what must be the case about this polynomial? This particular polynomial, which we call a trinomial, must be prime. Again, there is no pair of positive integers that multiply to 7 and add to 12. How about this one? All I've done is I've made the constant the linear coefficient and the linear coefficient the constant from the last example. But that changes everything. Is there a pair of positive integers that multiply to 12 and add to 7? How about 3 and 4? That works. 3 times 4 is 12. 3 plus 4 is 7. So it must be the case that x squared plus 7x plus 12 equals x plus 3 times x plus 4. Checking, x times x is x squared, x times 4 is 4x, 3 times x is 3x, or that adds up to 7x, 3 times 4 is 12. B squared minus 14b plus 40. See if you can figure it out. I need 2 integers that multiply to 40 and add to negative 14. Since they're multiplying to 40, which is positive, the 2 integers have the same sign. Since they're adding to negative 14, the common sign must be negative. Well, I'm just going to think about what numbers multiply to 40. How about 4 and 10? They multiply to 40, and guess what? Negative 4 plus negative 10 is negative 14. Voila! I have my factorization. B squared minus 14b plus 40 must factor into b minus 4 times b minus 10. Minus 4 times minus 10 is 40. Minus 4 plus negative 10 is negative 14. When I do my factor check, b times b is b squared, b times negative 10, negative 10b, negative 4 times b, negative 4b. My OI is minus 10 minus 4, which is minus 14b. Minus 4 times minus 10 is plus 40. Now, I probably was able to do that faster in my head than you're able to do it right now. But you know what? With a lot of practice, I bet you can do this just as fast as I can do it. I think that's pretty cool. How about y squared plus 2y minus 48? You try it. Okay, I need 2 numbers that multiply to negative 48, so the 2 numbers are going to have opposite signs, and I want those 2 numbers to add up to 2. Well, I know my times tables pretty well, and when I see 48, the first thing I think about is 6 times 8. And guess what? Negative 6 plus 8 is 2. I'm done, except writing down my answer. Y squared plus 2y minus 48 must factor into y plus 8 times y minus 6. Let's check. Y squared minus 6y plus 8y is 2y. 8 times minus 6 is minus 48. Okay, let's talk about factoring binomials. Let's factor, if possible, x squared minus 25. Something that can really be useful in math is if you can take something unfamiliar and turn it into something familiar. We've just been factoring a lot of trinomials. Can we make this a trinomial? Well, sure we can, if we go ahead and introduce a coefficient of 0 on our linear term x. So, can we think of two integers that multiply to negative 25 and add to 0? Well, I know I can, and I bet you can too. The two integers are positive 5 and negative 5. So it must be the case that x squared minus 25 factors into x plus 5 times x minus 5. Look at that from right to left. Remember, x plus 5, x minus 5, they're called conjugates, and conjugates multiply to the difference of perfect squares. So it makes sense that x squared minus 5 squared would factor into x plus 5 times x minus 5. Let's do that again. Let's think about y squared minus 49 as y squared plus 0y minus 49. Can you think of two integers that multiply to negative 49 and add to 0? I bet you can. They're 7 and negative 7. So it must be the case that y squared minus 49 factors into y plus 7 times y minus 7. Check. So 2 screens ago, we saw x squared minus 25 factors into x plus 5 times x minus 5. And on the last screen, we saw that y squared minus 49 factors into y plus 7 times y minus 7. I see a pattern here, and it hopefully is a familiar pattern for you, because as I mentioned when we were working with x squared minus 25, one of the special products that you learned when you were talking about multiplying polynomials is that the product of conjugates is a difference of squares. A plus b times a minus b equals a squared minus b squared. All we're doing now is we're taking this special product, we're using the symmetric property of equality, and we're turning it into a factor rule. And the factor rule is that the difference of squares, x squared minus b squared, factors into a plus b times a minus b. In the first example, a was x, b was 5. In the second example, a was y, b was 7. So let's use this. Let's factor t squared minus 100. What integer do you square that gives you 100? 10. So it must be the case that t squared minus 100 equals t plus 10 times t minus 10. I'll let you verify that one. How about x squared minus 5? Well, first thing we need to find is the integer that you square that gives you 5. There is no integer that you square that gives you 5. So over the integers, the binomial x squared minus 5 is prime. In later classes, after you've talked about square roots, you may see your teacher factor this using square roots. But square root of 5 is not an integer. So for the time being anyway, this binomial is prime. Let's factor, if possible, x squared plus 25. Well, let's use the same trick we used with x squared minus 25. Let's introduce a 0x term. Then the question becomes, are there two integers that multiply to 25 and add to 0? And hopefully you're thinking, are you nuts? Of course there's not two integers that multiply to 25 and add to 0. And the reason is because to get a product of 25, the two numbers have to have the same sign. And it's just not going to happen that you add two positive numbers and get 0, nor is it going to happen that you add two negative numbers and get 0. It has to be the case that x squared plus 25 is prime. It just ain't going to happen that you're going to add two positive numbers or two negative numbers and get 0. In fact, for positive real numbers b, x squared plus b never factors. You can bet on it. You don't even have to explore. X squared plus b never factors. Now, in a much later class, you're going to learn about some very funky different kinds of numbers, and you will learn that if you work with these very different funky kind of numbers, you actually can factor x squared plus b, but in almost all contexts, mathematicians agree that x squared plus b doesn't factor. So our conclusion here is that the binomial x squared plus 25 is prime. Let's factor, if possible, t squared plus 100. Well, we're adding a positive number to t squared. So what's the answer? The answer is the binomial t squared plus 100 is prime. Now, some of you are just itching to say, wait a second, this does factor. It factors into t plus 10 squared. Well, remember, t plus 10 squared is t plus 10 times t plus 10. And I'll leave it to you to FOIL out t plus 10 with t plus 10, and you will see that it is not equal to t squared plus 100. There's an I in there. There's an O and an I, and they don't add to 0. How about x squared plus 9? I'm adding a positive number to a squared variable. The binomial x squared plus 9 is prime. How about x squared plus 25x? Now you might go in auto mode and say this is prime, but this is completely different. I'm not just adding a positive number to x squared. I'm actually adding a linear term. You know what kind of problem this is? This is the kind of problem that Candace was working earlier in this lesson. X squared plus 25x, the two terms have a common factor of x. And when I pull out that common factor of x, I leave behind an x in the first term and a 25 in the second term, so this polynomial wasn't prime. Now I'm done with my part of the lesson. What Ann is going to do is she's going to mix up problems that like Candace did and like I did, and she's actually going to do several problems where she's doing both what Candace did and what I did, so I really think you need to go practice factoring some trinomials, if at all possible, before watching Ann's part of the lesson.
As promised, I'm going to work some more factoring examples. I'm going to start off by factoring trinomials using the guess and check method. Then I'm going to talk a little bit about factoring by grouping, and I'm going to end by talking a little bit about factoring some third-degree polynomial expressions. So let's start by factoring some more trinomials. So here's my first example. 2x squared minus 2x minus 24. This looks different from the problems you were just working with Steve, because the leading coefficient on x squared is 2. All the problems you were just working with Steve started with 1x squared. But one of the things we need to remember when we're factoring is that the first step should be to factor out any factor common to the terms. If we look at these three terms, we have a common factor of 2 to each of the three terms. So let's start by factoring that out. So 2x squared minus 2x minus 24. Factoring out the greatest common factor of 2 leaves behind x squared minus x minus 12. Now, when I write down the next step, I'm going to be factoring the trinomial into two binomial factors. That factor of 2 just lingers around. It's still there in the factorization. Now I'm going to ask, are there integer factors of negative 12 which add to negative 1? There are. Negative 4 and positive 3. So the trinomial factors into x minus 4 times x plus 3. I'm going to do a quick check. I'm going to start by checking that I pulled out the factor of 2 correctly. 2x squared minus 2x minus 24. That step's okay. Now, checking the product of these two binomials, x squared plus 3x minus 4x, that's minus x, minus 12. Looks like the factoring is good. Let's try another example. Now let's factor y squared plus 16y plus 64. The first thing we want to do is check to see if there are any factors common to the three terms. Well, in this case, the only factor common to the three terms is 1. Don't have to worry about that here. We just need to sit down and start factoring this trinomial. So what I'm looking for in this case are integer factors of 64 that add to 16. That one's pretty easy. 8 times 8 is 64. 8 plus 8 is 16. So this will factor into y plus 8 times y plus 8. And I can write this as y plus 8 quantity squared. Both of these representations are factorizations of the trinomial. Now when I check, I'm going to do something a little bit different here. Rather than using FOIL, when I do check my factorization, I'm going to use my special product. Remember, a plus b quantity squared is a squared plus 2ab plus b squared. Let's use that for our check. So I have a squared plus 2ab plus b squared. That's y squared plus 16y plus 64. That's exactly what I wanted. Now let's try factoring y to the fourth plus 2y cubed minus 63y squared. It's a good thing that we have a common factor here to factor out first, because this doesn't look anything like the problems we were just doing. So I'm going to start by factoring out the greatest common factor of the three terms. And what I notice is that each term has a factor of y squared. So I'm going to factor that out, and I'll leave behind a second degree trinomial. So now I need to factor y squared plus 2y minus 63. When I write my next line, that factor of y squared that I factored out just stays there, it doesn't go away. And now I'm looking for integer factors of negative 63 that add to positive 2. Well, positive 9 and negative 7, that will fit the bill. Here I'm going to do a quick check in my head. I'm going to first check the trinomial y squared plus 9y minus 7y, that's plus 2y, minus 63. That's this. Quick check to make sure I factored out y squared correctly. Y to the fourth plus 2y cubed minus 63y squared. It checks. Now let's do another example. 5x cubed plus 10x squared plus 80x. Here I have not only a common factor of x to each of the three terms, but also a common factor of 5. So I'm going to start by factoring out that greatest common factor. What I leave behind is an x squared plus 2x plus 16. At this step, I'm going to check, just checking the distributive property here, 5x cubed plus 10x squared plus 80x. Looks good. Now I'm going to try to factor the trinomial x squared plus 2x plus 16. So now I'm looking for integer factors of positive 16 that add to 2. 16 and 1, that doesn't work. 2 and 8, that won't work. 4 times 4, that won't work. So in this case, the trinomial x squared plus 2x plus 16 is prime. So at this stage of the game, I am done factoring the given polynomial expression. Let's try another example. Now we want to factor 2t squared minus 38t plus 180. Again, we're going to check for common factors first. In this case, we see that we have a common factor of 2 to each of the three terms. So let's factor that out. 2t squared minus 38t plus 180. Factoring out the 2 leaves behind t squared minus 19t plus 90. So now I'm looking for integer factors of 90 that will add to negative 19. 90 has a lot of integer factors, so I'm going to make a little table here, do some scratch work. So I'm looking for factors of 90 which add to negative 19. Both of my factors are going to have to be negative. So negative 1 and negative 90, well, that won't work. Negative 2 and negative 45, that adds to negative 47, that won't work. Negative 3 negative 30. That's not working. 4. 4 doesn't go into 90 evenly. How about 5? Well, let's see. 5 goes into 90 18 times. That's not going to work either. How about 6? Negative 6 times negative 15? Well, I'm getting closer to that product of, or that sum of negative 19, but I'm not there yet. 7 doesn't go into 90 evenly. 8 doesn't go into 90 evenly. But look, 9 does. And what do you know? 9 times 10 is 90, and negative 9 plus negative 10, that equals negative 19. So what does the trinomial factor to? T minus 9 times t minus 10. Take a minute to just check your factorization. Let's do another example. X squared plus 25x plus 10. So now we're looking for integer factors of 10 that add to 25. Well, when I see these numbers 25 and 10, I start thinking, hey, 5 plus 5 is 10. 5 times 5 is 25. Is that going to work? Let's look at this closely. We need our factors of 10 to add to 25. Some possible integer factors of 10 would be 1 and 10, that adds to 11, and 2 and 5, that adds to 7. This isn't going to work. So even though we have this tendency to want to work with 5s here, it's not what we're looking for to factor this trinomial. So what we see is this particular trinomial is prime. So the trinomial x squared plus 25x plus 10 is prime. So now we're going to look at something new, which is called factoring by grouping. We're going to start with a very simple factoring problem and just review what we would do when we were asked to factor 3x minus 12. Well, the first thing we recognize is that both terms have a factor of 3, and I can write that out explicitly. 3x minus 12 equals 3 times x minus 3 times 4. And then that common factor of 3, that's what I'm going to pull out. And what I leave behind is a term of x, that will give me the first term, 3x minus 4. That gives me the second term, negative 12. Here's another problem. Now this problem looks completely different on the surface, but it's really the same type of problem. Here I'm being asked to factor x times x plus 4 minus 5 times x plus 4. Well, just like in the previous example, both terms in this expression have a common factor of x plus 4. I can factor it out. If I pull out that x plus 4, what am I left with? Well, what do I need to multiply x plus 4 by to get the first term, x times x plus 4? Well, that's going to be an x. What do I need to multiply x plus 4 by to get the second term, negative 5 times x plus 4? Well, that's going to be negative 5. So I started off with this rather unusual looking expression, and I ended up with the product of binomials. Let's try that in another example. Same type of thing. I have a times the binomial a plus 3 plus 5 times the binomial a plus 3. Both terms have a common binomial factor, a plus 3. I can factor that out. Then I ask myself, what am I left with? Well, from the first term, I'm left with a factor of a. From the second term, I'm left with a factor of 5. So that unusual looking expression I have factors into a plus 3 times a plus 5. Now let's look a little bit more closely at this. Some students, when they see the expression a times a plus 3 plus 5 times a plus 3, see some factorization. But this expression is not factored. The expression has two terms combined by addition. There's still addition going on. In fact, we can see the addition occurring outside the grouping symbols. So that expression, as it was given, was not completely factored, which is why we went the extra step to factor out that binomial factor a plus 3. Let's do another example. Again, this expression is not completely factored. Now we have two terms combined by addition, and we can see the addition if we remember that subtraction can be changed to addition. When I look at this expression, I see subtraction going on outside the grouping symbols. The expression's not factored, so I need to do a little bit more work to factor it. As in the previous two examples we just did, when I look at my two terms in this expression, I see a common binomial factor of y minus 1. I can pull it out. When I factor out that common factor of y minus 1, what do I leave behind? Well, in the first term, I leave behind a factor of 2y. In the second term, I leave behind a factor of negative 3. So my second binomial factor will be 2y minus 3. If you wanted to do a check here, we're just going to use the distributive property. We're going to multiply y minus 1 by 2y, there's my first term, and y minus 1 by negative 3, there's my second term. Let's do this one more time. So now I have x times x plus 6 plus x plus 6. Well, what do I see here? I see the binomial x plus 6 occurring 2 times in both terms. I don't actually see a second factor in that second term, but that doesn't mean there is not another factor there. I could write a 1 there. There's always an implied factor of 1 in any term. So now when I factor out the common binomial factor, x plus 6, I leave behind an x from my first term and a factor of 1 from the second term. So now I have something different. And it's this problem that's going to lead us into a nice trick for factoring trinomials. I have 4 terms here. Now the first step in this factorization problem is to rewrite this expression so it looks like the problems we just worked. And all of those problems we started off with 2 terms with a common binomial factor. And this is where we actually factor by grouping. If I take these 4 terms, I can group the terms 2 by 2. If I look at the first 2 terms, x squared minus 3x, those terms share a common factor of x. When I look at the second 2 terms, 8x minus 24, those 2 terms share a common factor of 8. I'm going to work with this expression, working with these groups. So x squared minus 3x plus 8x minus 24. Factoring out an x from the first 2 terms leaves behind an x minus 3. Factoring out that factor of 8 from the second 2 terms, that leaves behind a factor of x minus 3. And look what we have. We have a common binomial factor of x minus 3. When I factor that out, I need a factor of x to get back my first term and a factor of 8 to get back my second term. Let's try this trick again. Here again, I have a polynomial expression with 4 terms. The first thing I want to do is check for common factors to all 4 terms, and I see that I don't have any in this case. So what I'm going to do now is see if I can possibly start factoring this by grouping the terms 2 by 2. So 2x squared plus 7x minus 4x minus 14. Looking at these 4 terms in groups of 2, I see that in the first pair of terms there is a common factor of x. If I factor that out, I leave behind a 2x plus 7. In the second 2 terms, there's a common factor of 2. But remember, Candace mentioned that in some situations it helps to factor out a negative. And this is one of those situations where that's very helpful. I'm going to factor out a negative 2 rather than a positive 2. So let's think about what we have. To get minus 4x, I multiply negative 2 by positive 2x. To get minus 14, I multiply negative 2 by positive 7. Now I have one of those kind of strange-looking problems with two terms with a common binomial factor. The common binomial factor is 2x plus 7, and when I factor that out, I leave behind an x from my first term and minus 2 from the second. Let's try it again. 3x squared plus 15x minus x minus 5. When I'm writing down the problem, I'm checking for common factors to all four terms. In this case, there are none except one. So I'm going to try this trick of factoring by grouping again. When I look at the first two terms, I see a common factor of 3x. I'm going to pull that out, and I leave behind an x plus 5. Now, it would be nice if when I factor a common factor from the last two terms, I end up with an x plus 5. I see minus x minus 5. Look what happens if I factor out negative 1. Negative 1 times positive x is minus x. Negative 1 times positive 5 is negative 5. At this stage of the game, I may want to quickly check using the distributive property, 3x squared plus 15x minus x minus 5. That's what I started with. Now factoring out the binomial factor of x plus 5, that leaves behind a 3x minus 1. Now I can use this trick in some situations where I have more than one variable. V squared minus u times v plus 10v minus 10u. Let's try to factor this by grouping. Do you see a common factor in the first two terms? I have a common factor of v. When I factor that out, I leave behind a v minus u. Second two terms have the second pair of terms has a common factor of 10. When I factor that out, I leave behind a v minus u. I have a common binomial factor of v minus u in both terms, and that leaves behind v, a factor of v from the first term, and a factor of 10 from the second. So we're going to finish off Lesson 9 factoring a couple of third-degree polynomial expressions. So here we have x cubed minus 3x squared plus 4x minus 12. These four terms do not have a common factor other than 1. So I'm going to try this new factoring by grouping trick to see if I get anywhere with this expression. So as I'm writing down my polynomial, I'm seeing some common factors. I notice a common factor of x squared that I can pull out of the first two terms. That will leave behind a binomial factor of x minus 3. I also see a common factor of 4 in the last two terms. When I factor that out, that leaves behind a binomial factor of x minus 3. Now in this case, this is really a happy coincidence. Typically, factoring third-degree polynomial expressions takes a little bit more work than this. But in this situation, we happen to have a common binomial factor in the two terms. I could factor that out, and it leaves behind x squared plus 4. Now I have to ask myself, am I done? Does x squared plus 4 factor? Well, Steve talked about this in his part of the lesson. When we see a sum of squares, like x squared plus 4, we can't factor that using real numbers. So we're done. Let's try it again. 4x cubed minus x squared minus 12x plus 3. Looking at the first two terms, I see a common factor of x squared. That leaves behind a 4x minus 1. Now, second two terms, I see a common factor of 3. But remember, I like to be able to leave behind a factor of 4x minus 1. I'm going to factor out a negative 3. When I do that, negative 3 times 4x, that's minus 12x. Negative 3 times negative 1, there's the plus 3. Factoring out that common binomial factor leaves behind x squared minus 3. X squared minus 3 is not the difference of perfect squares, so at this stage of the game, this is completely factored. One last example. We've been factoring by grouping. And when we factor by grouping, we've been working with 2 and 2, 4 terms. Here, we just have 3 terms, but we have a third-degree polynomial. So I'm hoping that something else is going to work here. Well, I'm going to start by looking for common factors. So remember, that's always the first thing to check, and it's actually a step that's easily overlooked. But here we notice that we have a common factor of 2x in all 3 terms. So factoring that out, I leave behind x squared minus x minus 20. Now think about the factorization of x squared minus x minus 20. Are there integer factors of negative 20 that add to negative 1? There are. Negative 5 plus positive 4 is negative 1. At this stage of the game, I want to check my factorization. I'm going to start by checking the distributive property here, 2x cubed minus 2x squared minus 40x, and then I'm going to check that x minus 5 times x plus 4 indeed equals x squared minus x minus 20. X squared minus 5x plus 4x, there's my minus x, minus 20. The factorization checks. So that ends lesson 9. We covered a lot of factoring problems in this lesson, so be sure to get a lot of practice before watching lesson 10.